Our last new rule for this section is the quotient rule. And if f and g are differentiable at x, and actually g of x is not equal to 0, then we can find the derivative of f of x over g of x by the following formula. F prime of x times g of x minus f of x times g prime of x. And then this is all over g of x squared. And we're going to try and use this right now. So notice the top function is x cubed, and the one in the denominator is x squared plus 1. And then let's find their derivatives real quick. That way we can just plug and chug. F prime of x is 3x squared using the power rule. And g prime of x is 2x. All right. So first of all, we want f prime of x, so that's 3x squared. Then we want times g of x, which is x squared plus 1, minus f of x, which is x cubed, times g prime of x, which is 2x, and then all over g of x squared. Let's do a little bit of simplification. Let's do some distributing. So we'll end up with a 3x to the 4th plus 3x squared minus 2x to the 4th all over x squared plus 1 squared, or x squared plus 1 quantity squared. Combining the x to the 4th terms will give us an x to the 4th plus 3x squared. And then this is all over, again, x squared plus 1 quantity squared. And you could try to factor an x squared out of the numerator here. It's not going to leave us with anything that we can cancel with in the denominator, so I'm going to just leave it like this. But let's give another one a try. So this one here actually looks like a product rule question. You have a product of functions and we want to find the derivative. There's one little issue, and it is this right here. So we cannot use the product rule because we don't know how to differentiate one minus x cubed to the negative 1. Okay, so we know how to differentiate things that look like 1 minus x cubed, right? And we also know how to differentiate things that look like x to the minus 1. But when we combine these two functions in this way, right now we don't know how to differentiate this. We're going to need to wait towards the end of the week until we figure out how we can differentiate something that looks like that. So for now, we're stuck with the quotient rule. Okay, and if you're wondering, well, how does the quotient rule apply to this problem? Well, if you have something raised to the negative 1 power, right, that means I could rewrite that as 1 over 1 minus x cubed. And technically you could write, to the 1 here, but that's unnecessary. I'll get rid of that. There we go. And if I do just a little bit more, this becomes cosine of x all over 1 minus x cubed. Now, we haven't done any calculus yet. We just got this to the point to where we can use the quotient rule. So let's see what that looks like. So we want the derivative of the top function, which is cosine of x. And when you take that derivative, you're going to get minus sine of x. And then we have times the function that's in the denominator, which is 1 minus x cubed, minus the derivative of the top function, which was cosine of x, and then times the derivative of 1 minus x cubed. Well, if we take that derivative, that's just going to be minus 3x squared. And then this is all over the denominator squared, which was 1 minus x cubed. Okay. Let's do a little bit of simplification, and we really don't have much to do here. I'm going to leave this minus sine of x times 1 minus x cubed. I'm just going to leave it as is. But this double negative I have here, I'm going to turn this into a plus 3x squared cosine of x. And then this is all over 1 minus x cubed squared. This puts us on to our last page, and we have 3 more examples that we're going to do. Let's take a look at this one. So, what I want you to notice is there are no variables in the numerator. If you ever notice that and you have a quotient, don't use the quotient rule. Okay. Here's why. We don't need to. We could rewrite this as 50 times z to the negative 3. And that, if we want to differentiate it, this is going to give us what? Minus 150. Actually, I'm skipping a step. I'll write this step in here. 50 times negative 3z to the minus 4. Okay, right? I just applied the power rule to this and then multiplied by 50. And this is equal to, how about minus 150 over z to the 4? And we're done. That's way easier than using the quotient rule. But if we use the quotient rule, we should end up with this exact same thing here. So if you ever accidentally use the quotient rule, it shouldn't cause any issues. But if we don't need to use it, let's not. Okay. For D, this is another one where you might look at it and say, hey, I want to use the quotient rule. But if we look at this one and think about this a little bit harder, we might see that maybe there's an easier way we could do this problem. Some of you might think about factoring here, which will end up resulting in the same thing that's going to happen here with what we're going to do. You might also think about, well, what happens if I split this fraction into 2? So we have 8x to the 6 all over 2x squared plus 10x cubed over 2x squared. And we can actually simplify that a little bit too, right? Each one of these. So the first one would be 4x to the 4th plus 5x. And now we could take the derivative. And all we need here really is the power rule. So I have 4 times 4x cubed plus 5 times 1. And if we want, we could rewrite this as 16x cubed plus 5. Okay. Before we do the next example, I want to point something out here to us that we maybe haven't thought of. If we had the reciprocal of the function that we started with, we would actually probably want to use the quotient rule. Okay, and this is because we're not going to be able to split this up in the same fashion, right? If I tried to do this, let's just think about why this isn't true. Okay, Okay, so is what I'm saying is these two things are not equal. And the reason being is if I did want to add these two together, I would need to get a common denominator first. And then if I did get a common denominator, when I added them, I wouldn't get 2x squared in the numerator. And you can see over here, by splitting this up, we do have a common denominator of 2x squared. So if we were to add them together, we know we'd end up with what we started with. Okay, so we can split up those sums in the numerator, but not sums in the denominator.